Our company was having issues with profile errors, and it would cause a lot of scrap waste for them. The waste codes that would fall under this were soft edge, hard edge, thickness out of spec, caliper variation too large, and gauge bands. So the goal of our project was to reduce the scrap waste weight from these waste codes by 20 to 30%.
Before we could develop our methodology for solving the problem, we first needed to make sure that the process and the measurement system used were capable. And so we performed a measurement system capability and a process capability analysis. Okay, so we performed a measuring system analysis on gauge system 1 and gauge system 2. Gauge system 1 is questionable. However, the data which we based our solution off of is based off of gauge 2. So we ran process capability on 7 different products. A process capability of greater than 1 is deemed capable with concern, and a process of capability greater than 1.33 is deemed capable with no concern. And so our core products, which are all above 1.33, show that there's no concern in terms of process capability.
We believe that having a mathematical relationship will be impactful due to the significant learning curve that occurs on every roll run. As you can see on the chart, roll number versus quality occurrences, there's a significant uptick in the number of quality problems at the beginning of a roll run versus the end. If we can shorten this learning curve to be able to reduce quality issues for operators by alerting them to quality problems earlier in the roll run, we'll be able to save a significant amount of waste.
The first thing we did when looking at the mathematical relation was put everything into a heat map. The heat map let us see the high and the low spots on the roll. From there, however, we could not determine where a gauge band was because it is not always at the highest or the lowest spot on the roll.
The methods we used to try to find the mathematical relation were finding the highest average sum for the columns, and then we tried finding the weighted average sum for the columns. Neither of those worked, and so eventually we moved on to looking at the difference between adjacent heights. And so if the difference between adjacent heights is greatest, it means it's likely there's a gauge band there. And so moving forward with the actual readout that the operators will receive, it shows the differences between the heights. The current readout that I have just shows the overall profile.
We were able to get our mathematical relation to detect 78.3% of the gauge bands that we had gauge band location data for. We then multiplied this 78.3% by a safety factor of 0.8 to account for any possible operator error or underlying gauge bands. This resulted in a 62.6% reduction of gauge bands, hard edges, and soft edges. We explored many alternatives for this project. This included regular die cleanings, glass purging, starting up with product A before switching to product B, new startup and shutdown procedures, as well as compressible core fillings, but nothing really came from any of these.
When deciding to design experiments for the chill roll temperatures and the nip pressure, we had initial hypotheses for why we believed this was going to be impactful. For the chill roll temps, we believe that the current state temperatures on chill rolls don't allow enough time for the material to smooth out once they come out of the die. Meanwhile, we believe nip pressure could be impactful because it would allow for the material to be pressed more firmly against the chiller roll when it was coming out of the die, allowing the profile to be smoothed out further.
The adjusted inputs experiment led to some interesting results. First, we learned that neither chiller roll temperature or nip pressure has a statistically significant effect on the number of gauge bands. However, chiller roll temperature does have a larger effect than the nip pressure. We also learned that decreasing the chiller roll temperature too much results in curling, and increasing it seemed to have a positive result in the number of gauge bands that occurred. For the nip pressure, we learned that we could not use too high of a nip pressure, or else it would lead to other issues on another one of their machines. Along with that, it would cause wrinkling near the edges of the rolls.
Based off the calculations on our results mathematical relation slide, we calculated a reduction of gauge bands, hard edges, and soft edges by 62.6% with the implementation of our project. Assuming a market interest rate of 12%, and an initial investment of $40,000, we have a net present value of over $390,000 with an ROI over 980% over a 3-year payback period.